I mean, we certainly could have written out changed the R in Coulomb's law so that we could write the integral in terms of rho and phi instead. How satisfying is that?
I need to learn how to do these integrals.
Because it's been a long time for me, so I was kind of struggling with what we were even trying to express until like Stoogie kind of like started on it. So I feel similar. I guess we could try a different problem though, unless we want to. We have anything else we want to talk about here?
I'm good to move.
Potential energy one. The first one, I thought it was 31. I'll go below. We just did. Oh, don't do this to me again, Discord. I have to leave and join the call. I don't know why it's doing this to me now. Okay. I gotta troubleshoot this off stream, I guess. There we go. 31. Okay. Decreasing energy. It's a 1-star problem. Hopefully we have better luck with this one. Hollow spherical shell with radius r is charge q uniformly distributed over it. The task of problem 1.32 is to show the energy stored in the system is q squared over 8 pi. Okay, we can just accept that. All charge concentrated into 2-point charge is q over 2. Okay, diametrically opposite positions on the shell. Ooh. Okay.
Do we even need to calculate anything for this? Or is it a reasoning question? Also, what is the reasoning they're asking for an error in? Or are they asking for us to find the error in their calculation?
I think they're just asking intuitively, not necessarily doing any calculations. Two. And these are going to be same sign charges. Diametrically opposite positions. That's going to be 2r distance.
Yeah, but I think the question is just a weirdly phrased, like, should the energy of the new system be greater or less than justify your answer?
So thinking about potential energy in terms of the work it takes to create the system. I would think that for a spherical shell with, a huge amount of charges in it, you could look at like each pair of charges that are opposite from each other, and it seems like you have to do. Oh, I guess they have less charge though. They have like less charge each. Okay, so that's a trick where they could be potentially close in value. But I was thinking we have so many more charges to bring in from infinity that just having 2 charges would be a lot less potential energy, but no.
Do we trust their new energy calculation, the energy of the new system? They say we can trust their first one. They don't say we can trust their second one.
True. That should be easy to calculate, though, right?
Yeah. Because it's just U new. It's Q times Q, which are both Q over 2 squared, or Q over 2. We can say K over 2R squared. Nope, not squared. Just 2R. Well, I guess they use 4 pi epsilon now.
Okay. Yeah, that's what they've written there.
Yeah, it's 2 to the 5th. Okay. Pi epsilon naught R. Discrete versus continuous? Maybe Phobos, yeah. Alright, Fembox. Sorry. Start with the same sound.
What happens if we do 4 points? Each one Q over 4 in strength. And they're placed like this along the edge of a circle.
It's an interesting question. We have, I guess, a bunch more pairs to consider. We definitely could.
I used big R. And then my thinking is that if we choose intermediate setups between the continuum and the discrete 2 case, then it should show a trend, I would think.
Oh. That's an interesting idea, almost like taking the limit.
Yeah, like taking the limit. I like that.
Yeah, so what will be going on there?
Or do you think it would be worthwhile to think about it in 3 dimensions? Because this is just a 2-dimension. And I don't know if 2 dimensions and setting up these charges is going to like change how the system behaves.
We do have more choices, I guess, in 3 dimensions.
Don't we have the derivation of the energy from a cube in the chapter? Because that could be 8 points on the surface of a sphere.
Oh. Yeah, that was one of the examples.
Ah, there's a charge in the middle.
Oh, dang. Okay.
DM extra charge if we just get rid of it.
Yeah. We don't like that charge. Let's just get rid of it to make our calculations simpler.
That's what they did with the cosines in problem 1.8.
Exactly.
About those extra terms.
Bye-bye. Yeah.
I saw the author with the broom sweeping them under the rug. I'm not sure what to do with that. What do you all think is worthwhile? Or do you have any alternative ideas for kind of explaining what happens between these two configurations.
So if one, I'm trying to like think about which one is more stable, right? If if the energy decreases, is that good? Do we want that? It means that there's less energy, or it takes less work.
I don't feel the urge to try 1.32 first, I guess. Like, we can just take this as a fact, like the problem says Finbox. Unless we want
I feel
to,
like
but
1.32 is going to need an integral.
yeah. I'm trying to think about it in terms of like the work. To make the new system, you would hold like one of these charges at the same point, and the other charge you bring it in from infinity. Um, Whereas, how do we create this sphere? We,
You just bring in each DQ.
yeah. If that's our favorite charge right there, we bring in like a DQ there, a DQ there, a DQ there. I'm working like down below in a new thing, kind of. Or like just below. It's not really that helpful yet, though. um,
Do you think it takes, or rather, there's potential for the system to enter the state of 2 points being at the end, and you can think about the sphere kind of like unrolling from itself in the periwinkle
Yeah.
picture, kind of unrolling itself into the 2 points.
oh,
And then if we can argue that the circle wants, or that the energies involved, or the potential energies involved are such, then we could argue that energy, or right, the appropriate flow of energy could take all the charge from the surface of the sphere and migrate it to the points on the side. So we can go from a high potential to a lower potential through some physical process.
Right.
yeah. If I take this sphere and I cut it in half, symbolize like what you said with the two things, like the distance from, if this is our favorite charge here, what we have in the new case is just this longest possible distance on the opposite end. But with the actual sphere, we have a smaller distance like diagonally there, smaller distance diagonally there. So since we're bringing it we're bringing it closer. So that is more work to bring it closer.
I'll buy it.
So it makes sense that the new system has less energy, I think.
I think that makes sense. And something that's going through my mind about it, or another potential interpretation of it, is imagine you took the two sides of the sphere. I'm to the right of your
Oh, I see it, yeah.
picture. Imagine the sphere is perfectly conductive, like a superconductor, and it's got a charge over its surface, and you separate the spheres, and then they're both charged. I think that they would naturally separate from each other since they share the same charge towards the points furthest from each other.
Okay.
So if these are covered in static electricity, you cut it in half, they're both positively charged, let's say, then they want to get as far away from each other in terms of charge as they can, and that should migrate away, if you have a tiny, just little distance here, dx, delta x, whatever you want to call it. That might be one other physical interpretation.
So they're trying to push away from each other, but how's it different from the point charges pushing away? I missed that part, I guess.
I'm thinking of the charge distribution over the whole sphere kind of migrating away from being over the whole sphere once you separate these sides from each other. So now that it's free not to distribute itself evenly over the sphere, it should choose a lower energy configuration, which should be those 2 points away from each other, which we calculated up here. But that relies on it's a superconductor, it's statically charged.
Interesting. Yeah, I'm still trying to like figure it out, but it seems like it might work.
Yeah, that makes sense to me.
Okay, that's kind of nice, just like reasoning one then. How difficult does 32 look? Or we just
I'm gonna look at the answer for this.
Oh, that's a good idea.
Just what the book thinks is a good physical reasoning here.
Do they have the answers for these ones? I thought they stopped at a certain.
After 33, like 33 is the last one with an answer, I think.
Oh, then we're on our own. Hell yeah, I can look at the one that I did. Make sure it makes sense. No, wait, I can see what they did.
Doesn't
see why mine doesn't make sense.
No.
Did you just say we're wrong, stupid? The whole time.
Oh yeah, so 32 is definitely an integral. I'll take a look around, see if we can just like maybe do some, because like it did seem like there some of the problems or whatever the last part were that there's like 1 or 2 stars that wouldn't be as intense as that first one we did.
Did the book start with a 3-star problem? Because that's fun.
Did the book start with 3-star?
Yeah, was that a 1 or a 2? No, it's probably a 2.
The book, the very first one is just the 1 star for gravity versus electricity. I think we did that one. It does get in, like, number 8 is a 3-star. That's early. Ron Stoppable, thanks for the follow. Good reference. What did like 56 and 58 look like? Oh, let's not do that. Or that. Actually, maybe there's like a field one. Sorry, what?
Nothing.
Okay.
I think we did number 31 wrong.
We did 31?
The wrong conclusions.
Oh, I wasn't looking at the answer for 31. Is there a flaw?
They say it don't make sense.
Oh, no. All right, well, let me go to it.
Oh, yeah, if you could copy paste it into the thing, we could probably point at it.
Oh, sure.
And laugh at our ineptitude. Look at us trying to reason about electricity and magnetism.
Looking for it. 31, 26. No, it doesn't make sense. Okay. Hopefully the text will copy in so I don't have to bother taking a screenshot. Oh god. How do I make this like... Oh, I just literally drag a corner. Okay. Can I... Okay, there we go. Yeah, this is a little answer from the book. No, does it make sense? The point charge configuration should have more energy. What? Assuming it is constrained to remain on the shell? Wait, when did we make that assumption?
I mean, I assume they were going to stay on the shell. We're working with statics.
I guess so. Infinitely more energy. Include their self energies.
And have we dealt with self energies before? Because like we've had point charges, and I think this is the first time I've heard self energies.
Yeah.
Maybe not. They say a example in section 1.15.
Okay, yeah, so it takes a lot of work, I guess, to have compressed those two halves of the sphere into point charges. Which, I guess that's fair. They did say that.
If you think about it that way, I was thinking it's just 2-point charges.
Yeah, that's what I was thinking of too, but they did say taking all the charge and concentrating it, which I guess was the key. Huh. They were truly point charges when I'm smeared out over the sphere in the first place. Yeah. I just didn't read the question carefully enough, or I was taking two entirely different situations that happen to have that relationship with the radius and the total charges. But yeah, they're saying you physically like take that sphere, each half and somehow concentrate it. But if you did have just like two entirely separate situations, I think this would be true. Okay. Well, I'm glad.
Yeah.
Oh, what?
Somehow it seems like the energy must be measuring something, or this U must be measuring something different, right?
It should be potential energy.
Yeah, the like the work integral and the stuff that like I wrote with like U sub nu is if this Q over 2 to our situation happened in a vacuum, like we're not, like I assume we brought out one of the charges out from infinity, but we're not. We're bringing a charge on this spherical shell into its corresponding like point charge or pseudo point charge, which is a different integral. That's gonna, I guess, approach infinity the closer they get. Okay, I do see kind of a neat one that we could maybe, depending on how long it takes, wrap up with. That shouldn't involve integration if we want a little mental break from that at least. I guess let's start a new whiteboard. View boards, create new. So we might need to toggle over to this one in the upper left. Chapter 1, part 2, -2. And I have to rejoin the call every time I do a new image. Annoying. So this is number 40. It's one of the ones without a solution.
It's better that way. We won't know if we're wrong.
Yeah, exactly.
We can have confidence in the answer. I feel good about it, and that's all you need.
Love it.
If we all agree, then we're good. I'll never
just
disagree.
live in denial.
Oh yeah, it's the best.
Yeah. Okay, do you all see the new board and the problem that I put in the upper left? You have to actually like click over. You're good, Suki. Phyllis, are you able to find it?
I see 1.40.
Awesome. Find a geometrical arrangement of one proton and two electrons such that the potential energy of each system is exactly 0. Which I guess is kind of related to that one triangle problem.
Hey, didn't you do that earlier, Doug? On stream?
Did I?
Let's go. I thought you did one that was similar. Maybe it was just 2 charges. One with had double charge of the
Oh, yeah. This is a different one. I remember that one now. Geometrical arrangement of one proton and 2 electrons. Potential energy is 0. So what comes to mind first, oh god, is positive in the middle, or I guess proton in the middle, electrons equidistant on either side. Is that 0?
I think it can be with appropriate distance between all of the things. And I think it would be symmetric in this case. Because you have the attractive force of the proton and the repulsive force of the electron on the other electron. So it should even out at some point. Wouldn't it be funny if it was supposed to be like this?
Good thing there's no answer key, so we can just say this is the right answer.
All you gotta do is you gotta believe in yourself. And since they need to just be on one line, that should keep the equations pretty simple. We should be able to do this with the potential energy equation. And there are 3 terms that we'll need, correct?
Right.
So like U would equal KQ times an electron and an anti-electron, or proton, whatever.
It's all the same.
Physics.
Yeah.
And an electron and another electron. And we just got to figure out the denominators and stuff.
Yeah, I guess for the first one, it should just be R. We have to multiply the entire thing by 2.
Is it Q squared, Fembox?
Well, why do we have
Right.
Q and E?
Right. Q goes away.
Yeah.
Because E's are doing their thing. They're hanging out. They're having a good time. Okay. And then in the picture. Oh goodness. We need coordinates on all these things.
Oh, I mean, I guess we could take the positive one as the origin.
Yeah, that's what I was thinking. So if you're at 0, there's distance x1 to one of the electrons and distance x2, and it's sign distance. So
Okay.
this one would be negative x2. Let me switch that arrow. Because it could be that you could have both on the same side. Wouldn't that be something?
I'm worried that there's more arrangements,
that
but
it is signed distance. I think it's unsigned distance.
Okay. I can dig it.
I think so too. Or I guess what
Use
does it come out to be if
unsigned.
we just use R? Yeah, or X or whatever we want.
Shoot, what goes in the denominator? It'd be x1.
Yeah, just the next one, I think.
And that's between the proton and the electron. And between the proton and the other electron, it's x2. I don't know how you want these. Absolute values or no. I'm going to put them in absolute values.
Yeah, why not?
Just because. And for the electrons to each other, though, we need an expression for that. And I think that's where we get two cases. If the electrons are both on the same side of the proton, then that would be one configuration, and when they're on opposite sides, it would be another. Does that seem reasonable, or do you think that there's only one configuration for what we're doing?
If they're on the same side, can we ever have zero potential energy?
Oh, that's a good point.
If they're equal
No.
charges, no. Yeah.
Yeah, because the positive is always going to get attracted. I mean, you might get lucky with the other two charges, but
Yeah. If this positive charge was like 2E or something, we might be talking. But if they're all
well, it's
equal,
still going to get attracted.
um,
If you have
oh yeah, okay, you're right.
right, I don't know what the yellows are going to do, but I know the red is going that way.
I guess yeah, the middle yellow will get pushed into the red. Okay. I guess the forces can only sum to zero if they're collinear. Oh, that's fair, Fembox. Yeah, vectors wouldn't work out otherwise. So does thing that Phobos wrote come out to be zero?
We have to find x1 and x2 such that it does, I think.
Would they not be equal? I was kind of assuming that.
Yeah, they have to be equal because otherwise the proton's going to go one way or the other.
Oh yeah, okay.
That's not very exaggerated.
Yeah, because whichever pairs are closer will smash into each other.
So you say x1 is x2 in the equation.
I think so.
So we get, I'm going to expand all these terms and get the negative signs correct. So we get negative e squared over x1. Or I'll use r like y'all have used. That's fine too.
It all works.
And then we'll have two of those, actually. Oh boy.
Yeah.
This shouldn't be the hardest part, to erase something.
I
We're doing it.
just click on it and hit delete. It's kind of weird though, yeah.
Yeah, that just straight up doesn't work for me.
Oh, okay.
2r.
Got booted out of the activity somehow.
So does this look a reasonable second step from what we had before?
Yeah.
I'm worried it's not zero, but yeah.
We need to find that it is 0. We need to believe in ourselves, Don.
Okay.
We need to manifest a 0. And we have a positive and a negative term. We should be able to modulate the radius, perhaps, to get them to be equal. Right?
Yeah.
So, let's see if we can do that. We should end up with 2e squared over big R equals e squared over 2r. Slash in the e's. You don't need none of that. Don't need none of these r's. That don't seem right.
Yeah.
2 equals a half. Did it. All right. What do you all got?
It should depend on the actual value of R, because you could always like take the same system and scale it up. I remember the book made that point in a different problem. I think it was one I saw Stucky do. If I'm remembering right. Like this thing should be 0. That was actually, yeah, what was that problem? With the there's one linear case and one triangular case.
Yeah, it's 3, 4.
Let's see, it's number 6.
Well, all right.
I mean, that's approximately 6.
Yeah.
And it lets me, okay, good. My screenshots are still working. I'll just get 6 in here. Because I remember for this one, I looked at the answer key, and they did say you can just like scale this this system. I have 3 separate screenshots for this one because it was a lot. Equilibrium implies u equals 0. U equals 0 doesn't imply equilibrium. It could be an unstable equilibrium. I feel like that's still an equilibrium, though.
It'll never last, Don.
Oh, that one's getting what Q should be, so it is an equilibrium. And that, yeah, that wasn't, these weren't, that was like Q over 4, something, if I remember your work right. Small Q over 4 for big Q. So we did, if they're all equal, can they not be collinear? Unless we're saying this U equals 0 is an equilibrium thing.
Yeah, I guess we gotta roll with it.
Like what other arrangement could we possibly have? Because I think I think we can eliminate the straight line case based off what Phobos has here.
Well, do we agree with the setup? I feel like there could be other setups that could potentially give you 0 potential energy. But I don't know for sure.
Yeah, very possible.
For instance, just putting them all on one side somehow. Maybe put one of them at infinity. That'll never work. Then the two that are not infinitely apart will always go towards each other.
It's true. Mox is pointing out there's a 1.5 connection. Oh, that's not the problem that I thought it was, but okay.
Oh, I don't think I did 1.5. Wait. Oh yeah, it was 1.7 that I did.
Did I add the right number of pairs here? Should be 3 pairs, right? There's...
Yeah.
Yeah, I agree with your setup there. And I feel like we've eliminated them all being like 2 negatives in a row and one being closer to the other. So
Here's the thing. Here's something going through my mind. Imagine you have just 2 of the charges, positive and negative, and then the challenge is put the other negative charge somewhere to create equilibrium. And then I was like, all right, but then you're only adding 1 more interaction to the system, right? Or is it 2? No, you're adding 2. I take it back.
Right.
It makes sense to me now.
But again, 0 energy. I feel like we should drop the R assumption and check that you can't get away with putting the proton somewhere else. I mean, somewhere in between them. That's not right in the center. And then try the other one, right? It's not out of options yet.
Okay. Well, let me think about that. Are you still thinking proton in the middle of the 2 charges, but not equidistant from both sides?
Yeah.
That's what you're thinking? Okay. Ah, Fembox.
Hey.
Hey, hi.
How's it going?
Doing good. Can everybody hear me?
Yeah.
Yeah.
Oh, nice. My microphone must work. So I had a cool idea. I don't know how to get on the whiteboard. I don't know if I need to, but if you take the 2 electrons and just consider them fixed for a minute, right? At the end of a line segment. Then what you could do is consider moving the proton, right? So the 2 electrons are fixed. And now we move the proton, and we should be able to find a point we can move it to. Yeah, I see what Don's
like
doing
in
there.
a triangle like that in the middle? Or a
yeah,
right
and
triangle?
you could find a point right there. So, you know, call the distance between the 2 electrons, call that R maybe. And then we should be able to find the distance of the proton from the midpoint of that line segment R, such that U equals 0 for the system, right? That we can do that. And then the cool thing is, if you let the so by symmetry, you'll get another point underneath.
True.
But then the cool thing is, we'll get some kind of a curve in the plane that will go through those 2 points, and it's an equipotential, right? So it's all the points where the potential energy of the system equals 0. And so there will be points actually on the line that joins those 2 electrons. There'll be a point to the left of the left electron, and there'll be another point over to the right of the right one, where the potential of the system will be 0. And I think they're telling us that that's going to be the golden ratio. I think that's what the question said. Anyway, we'll be able to prove it.
Okay. So I guess, oh gosh. The U for the negative pair is just E squared over, or KE squared over R.
Yep.
And we're going to set that equal to I guess consider the pair as a unit, or I don't know exactly how we should like note this, but I'm just gonna call it U positive. Well,
Sure. Yep.
maybe. Okay, fine. Yeah. We're going to take H. I guess H would be a variable that we solve for.
Yeah.
So the distance is going to be root r squared over 4 plus h squared. I promise that's a 4. If we do Pythagorean theorem.
And if you take two of those
Right.
negative ones and add them, sorry, two of the positive ones and add it to the negative one and set it to 0.
Okay, yeah, that's a better way.
We can solve for h, right?
Okay, yeah, that's nice.
This is great. I thought we were stuck in a line and that we had to use a line for this.
I did too, you know, because I was misunderstanding the question. I thought we were trying to find where it was going to be an equilibrium, but you know what? I don't think there is any way to have 2 electrons and 1 proton in equilibrium.
Doesn't seem like it. I guess it doesn't mean potential is 0, like you're saying. Oh, this isn't. Oh, it is rooted. Okay, never mind. Equals 0. Okay.
Yeah, because that question 1.6 we did, you know, we had the symmetry with 1 point charge in the middle, but the question was sort of asking us, how big does the capital Q in the middle have to be so that we can get equilibrium? And it turned out it wasn't equal to the lowercase q, right? It was bigger. Or was it small? I think it was smaller.
I think smaller, yeah.
But then
It's h squared. Fractions. Number 4. A terrible order to write things in, but root 15 over 2r? It's a number.
or why not?
Not in love with it, but okay. So the question is find a geometrical arrangement of 1 proton such that the energy is 0, which I guess we found 2. How many such arrangements are there with 3 particles on the straight line? 0. Then find
Well, no, there will
Are there?
There will be. Yeah, there will be.
I thought we just said there weren't.
There's nothing, there's no way to get the system into equilibrium, but to get it to have potential energy 0, there's going to be a continuous way we can move that proton around in some kind of and I only know this because I messed around with this on Desmos, and it was so surprising to me when I plugged it in and I sort of set a slider, and I moved the slider to change the potential, and it was so cool how the things were moving around. I tell you, I got to post it on your Discord so you guys can look at it. But
Oh, please do.
yeah. But you know what? Just take that positive charge there and move it over. Instead of having it above, just move it over so it's on the same line with the 2 electrons.
Oh, and do the same calculation?
Yeah, and we can do the same kind of calculation.
I guess I'll call it H again for consistency. It's like, are we gonna get like an ellipse out of this?
I don't know. It might be. It might be an ellipse.
Where the negatives are the foci. That's my guess at least, but I guess we can
Wow.
get a few more points. So we have KE squared over R minus 2KE squared over... Oh, well, now we have two different distances, don't we? H minus KE squared over H plus R equals 0. Okay. H plus R. R. H plus R. Minus RH equals 0. I think I did those fractions right.
Yeah, that's good.
RH minus RR minus RH.
Same arm?
What am I? Yeah, what? Oops.
Oh yeah, there's no big and little, right? It's the same one.
I just love adding more variables for no reason. R, oh my god. Throw it out. H equals 0. Those cancel. Minus RH minus R squared.
Complete that square.
I'll complete the square?
Maybe. No, I don't know. I don't know if that's
Oh,
gonna happen.
okay.
It's something you can do. It's something maybe it's possible.
I was just gonna try the quadratic formula.
Oh yeah, check that out.
Plus 4R squared. That seems like, oh, oh wait, is it the golden ratio if R is 1?
I feel like you can pull out an R from those numerators.
Mm.
Yeah, I'm just thinking like I think the polynomial that goes with the golden ratio is x squared minus x minus 1.
Yeah.
So it'll make sense if, okay, yeah. R squared plus or minus R root 5. Yeah, that looks pretty golden ratio E. Well, almost.
Just R
The
that first
ratio
one.
between the distances.
Oh god, I had it squared. Sorry, what?
Okay, yeah. Nothing. This is
Okay.
good. This is great.
I guess yeah, R times the golden ratio for this. But why didn't we take? Shouldn't we have gotten that over on the right? I wonder if I made a mistake on the right.
The question was asking about the ratios in the straight line
Oh,
specifically. So I think that it doesn't
Oh,
necessarily
cool.
have to be the same answer.
okay, good. And if it is an ellipse, that wouldn't make sense anyway. That's neat.
So what we could do, if we wanted to, and I don't think we want to right now, but you could set the coordinate, so you could put the origin halfway between the two electrons, right? And then you could let the coordinates of the proton be x, y, and you could do all this in terms of x and y, right? And that's kind of what I did on Desmos. I got a potential function that was a function of I forget how I did it. It was a function of two variables, and a potential function that depended on x and y, and then I plotted it, and I just did a slider for what the total potential would be. And so we could do something like that. And then if you set the slider equal to 0, you know, you'd see the solution curve that was, yeah, where all the different places the proton could live where the total potential was 0. It might be something like that. I don't know.
Yeah. A proton amoeba. I wonder. I feel like this one site might be able to do it. That physics and depression showed once. See if I can maybe try and make it quick. So I think there's a setting for like equipotential lines or something like that. That might be what this thing is asking for. Which one is it? Okay, that looks like something. Show equipotentials. We need another charge. Hey, Bladwee, yeah. Oh, how do you toggle the charge of this thing? Edit. Minus. Okay. Oh, wait, we need to... Minus. Okay. Potential. Ooh. I don't know what this means, to be honest. It looks cool, though. I don't think... Huh. I assume... Yeah, I don't know.
Yeah, I don't know.
I think there's something to it. I don't know how to interpret it, though.
For a
What?
test charge. I think it's showing potential for a test charge in that configuration.
Oh, is the ratio not right?
I don't think that it's a ratio problem. I think that the field that they're showing is for a test charge, not the potential for the system. So the
Right.
redness
Oh.
is the potential if you had a test charge there.
Oh, that makes sense. What if I got rid of this thing? This positive one. Oh. It's like a lizard eye.
Is there an example? Is one of the examples triple charge?
Let's see. Single dipole. Oh, man. Oh, it's not showing up on stream, this drop down. It's only single charge, double charge, dipole charge, and then it gets into like planes and cylinders and objects like that. I don't know. If anyone wants to play with it, I'll put the link in chat, but
That's a nice website.
yeah, that's a bunch of things. I'm trying to like learn a bit more because I think it might be helpful for this, but yeah. Funny though, I wonder what kind of shape that this would make. I'm sure that's like a term that we could search and just like find it, but okay. I guess we did 40 then, unless anyone has anything to add to it.
Who needs a solution manual, right?
We got Fembox. I don't know, I guess maybe we'll wrap things up for the reading group there, since we've done about 2 hours-ish. Is there anything else for the good of the order? I might go do some math help. Thank you.
I mean, presumably we're gonna keep at chapter 1 for another week.
Oh, that's a good... Yeah, we should figure that out. I think doing another week on chapter 1 wouldn't... I think it'd be a good idea, right? There's still some cool looking problems that we could do. So yeah, unless there's any objection, let's keep on chapter 1 for another week, and then after that we can move on. And I guess I'm not hearing any, so...
Yeah, sounds good.
Okay.
Sounds good.
Awesome. Well, thanks for, I guess, coming here for another Saturday. It's nice to actually talk to you, Fembox.
Yeah, really nice to meet all you guys. I mean, it's kind of weird because I've watched all your streams so many times, and so I feel like I know you and you don't really know me. But anyway, hi.
Well, feel free to pop in. Hello?
All right. Take
Okay.
care.
Sounds good.
Bye-bye.
See ya.
See ya.
All right, cool. You posted a bunch of questions. Okay, let me get things switched over. Critical. Get some music playing. There's like an hour in that I forgot to start the YouTube stream, so Geometric Power Series? Okay. Chat and internet. Math. Okay, Twitch is updated. Let me go update YouTube. Where's my YouTube information? Yeah, it should just be a minute or two. Oh, what am I doing? Go there. Fun problems though. That first one that we did was like, oh shoot! I wish I want to see what parameterization. Oh god. They use it in the books. I feel like there's probably an easier way to do that. Okay, updated YouTube. Okay, I'm gonna look at one thing critical, and then I'll look at your questions. And if you do leave, I'll at you. It should only be a couple of minutes, though. I just want to see what the answer key was for that. What question even was it? Um, 15. Oh, that's they might skip over some steps. I just like saw the number of lines. It's like zero net flux. We did get it right, yeah. I mean, I guess getting the same answer for each version is a nice like confirmation, but I'm just certain how they did it. They reduce it to a single integral, I guess because they get this cosine beta term geometrically. Q over 4 pi epsilon naught r squared. They observe that r squared is equal to L over cosine beta. Sure, that's what we did. Except we called it alpha, but this brings in factor of cosine beta, yeah. Oh, we got that from the dot product, which I guess is where they get it to without saying it. Well, eh. Hey, Croc. I'm doing good. Thanks for asking. If I ever did optimization, I did optimization that you would encounter in like a normal Calculus 1 or Calculus 2 class. I've technically done like Lagrange multipliers in a multivariable calculus class. I feel like I've seen you ask maybe some more advanced questions than I've been able to do. So if you're doing anything that you wouldn't encounter in a normal like calculus class, I probably can't help you. I've never heard of Fenchel or Fenkel. No. Unfortunately, I don't know who would have either. So, is music? No, music's at a good level. I think it's just volume on my end. A constant. Oh, considering the rings, that might have simplified how I was thinking about this 2D thing. Because yeah, we were just doing like a small patch, but we could have done it with rings, I guess. The total area is 2 pi L tangent. Okay, so that's just circumference of a circle. Wait. Oh, it's the area of a circle derived. Okay. If the ring subtends an angle d beta. Differentiated. They also derived it, you know. They derived this equation and differentiated it. They derived it by differentiating it. The ring subtends an angle d beta. So yeah, it will be the circumference of a circle times just a little like thickness of the circle, I guess, to make it a ring. The rare case you can get away with that argument. Yeah. They say that the derivative of tangent is 1 over cosine squared, and that throws me off every time because I expect to see secant squared. It's the same thing, but I have to think about it every time. Total flux through this disk. What's happening? This is the field. Q. Oh, okay. And then the cosine squared up top comes from the R being L over cosine. So the cosine flips up. And then they dot it with dA, which is what we just looked at. So the cosine squareds cancel, the L squareds cancel. Did we get exactly Q over 2 epsilon naught? I feel like our coefficient was slightly different. Before I forget, I need to go and actually grab those whiteboards that we just made. I'll put them in the reading group. Chat. Copy. Chapter 1, Part 2 notes. Paste that in. Copy. Paste that in. What's in terms of K? Well, K is 1 over 4 pi epsilon naught. Oh, we got 2 pi times K. Okay. And that works out. Okay, cool. I just want to sure like I wasn't off by like a factor of 2 or something. Or I have a very short. Hey, iBreezy, welcome in. The integral of x to the power of dx is not a thing. I have no idea what it actually means, but I've seen people say that's a real integral. I Oh man, I would need to ask Penn Center, or because I think Penn Center has done an integral like that and might know more about it than I do. I mean, we can Google it. X to the dx. But Penn Center's another math streamer if you're new to the Twitch math community. What's that, Pladwy? I don't know how you interpret it geometrically. Oh, Google isn't quite working for that. So a video on it? Oh, okay. Oh, God. I guess that makes sense. Yeah, so what he's doing, he's multiplies by dx divided by dx, and then notices that this thing looks like the definition of a limit. So I think it's a real thing, iBreezy. I don't understand it for myself, I guess, but it's just the integral of ln x. Wow. I feel it's more of a notation trick than anything particularly meaningful, but yeah. It's not exactly mathematically rigorous. Yeah, I can agree with that. Oh, using a Taylor series, wow. I don't. This person makes the claim that you can do this rigorously, even if his explanation isn't. I'm not the authority on this, so you shouldn't take a yes or no from me to be the end word, you know, to be the last word. My impression of this is that it's more of a party trick than anything that's like than something that's actually profound. Yeah. And hey, Ishan, I don't know how to do those problems. I'm sorry. These are the YouTube thing. What the hell does it even mean? I think it really just means the integral of ln x dx, but someone found some super weird notation way to rewrite that. But yeah, in a vacuum, the integral of x to the power of dx makes no sense to me as someone who only knows what a Riemann integral is. There are other types of integrals, but I doubt they deal with that case either. But I would just say, according to that YouTube video at least, it just means the integral of ln x dx. I think that's an unsatisfying answer. I think it's just some neat trick, I guess. I might be wrong on that too, but I wouldn't like. It's probably not like a. I don't know. I don't know how to explain it, but I don't have a lot of respect for that thing as like the holy grail of doing integrals. It's more like competition math, maybe, where you're just doing things for fun. Rather than things that are that helpful. Okay. Looks like we got our I think our parameterization, it was definitely different. I kind of like the books feels a lot more direct. It's less geometrically intensive. But we did find another way to do it validly. I think it's just being obtuse. I breezy. I mean, having skimmed through a single YouTube video on it, it would be like, it does mean something, but it's like, I'm gonna do my entire math homework, but instead of writing 2, I'm instead going to write 2/3 times 3. You're just making it more complicated for no reason. This still means 2, but why would you ever bother doing this? I would put that on the same level. Personally, but my opinion means very little on that, I think. Okay, you learn all their dirty tricks? I mean, physics integration is simultaneously really difficult and really easy when you just get to throw terms out for fun. So yeah, I breezy. I think that's how I would call that. All right, we gotta get through some critical questions here. Let me add critical in case they're not, in case I have the stream on mute. Some way to make it mean something. I mean, I just don't really care enough to think harder past it means the integral of ln x dx. If it's possible there's something more important to it, but I don't know what that thing is. Power series representation for a function, determine. Oh, thanks for the follow. And if you ever find yourself having more math questions that I'm not around, I should give a general shout out to some of the other math streamers that I can recommend highly, as well as to Hobostream, who isn't in that list, but. Yeah. Yeah, I breezy. There's a whole bunch of like weird math things on the internet that are potentially like true but not useful. They're yeah. Hey underscore. You're here? Okay. So you were talking about a geometric power series at some point, critical, or are we going down the list and doing all of these? Oh, yeah, this first one is, these probably, yeah, these first 3 are all like a geometric series. I haven't considered the rest of them yet. So everything is, okay. And you said you don't know what a geometric power series means in the first place? So I can talk about that first before I even do a problem. You have the yeah, exactly that. So yeah, if your sum of a geometric series is a over 1 minus r, it's an a, not a q. If you happen to get a function that's like a number over 1 minus your variable, you could say that that's the sum of a geometric series. And that's kind of the idea that they're using here, where instead of r you have x, but you can say x equals r. And that makes it a power series. But you might, we don't usually have a situation that's that clean as 1 over 1 minus x, so we have to do some kind of transformations here. Convert it to a, yeah, exactly. So our first question is we have f of x 2 over 3 minus x. So yeah, we want to do anything that we have to make it match a over 1 minus r. And the issue here is that 3. We need that 3 to be a 1. Okay. Sorry about that. I put my mic on the charger the last time I streamed, but I guess I didn't plug it in all the way, and then I charged it for like half an hour before the stream started when I noticed that it wasn't actually charging, but I guess half an hour wasn't long enough. We're going to paint. It's a little weird. I don't know why. I don't know why the top part of it is so weird, but it's fine. Okay. That's annoying. So okay, so let's just go back through the problem because I don't know exactly when my mic cut off. But yeah, if we have a series like this, we have to do anything it takes to get it into the geometric form, a over 1 minus r, as you said. And the issue here is the 3. And thanks, Fenbox, for playing that sound. So we need to deal with that 3 any way we can to make it into a 1. And the easiest way that I see to deal with that is to factor it out from the bottom. And this is technically good to go as it is, but I'm going to make it a bit more clear what's a and what's r. And I'm going to take this little bit here and write it as a fraction in the numerator, which is completely allowed. It's not changing the actual value. And you don't actually have to do that if you don't want, but I am trying to make it like clear why we are now in the a over 1 minus r form. And we know what a geometric series looks like since we know what A and R are. I always forget. These things, it shouldn't matter if we start, as long as we're consistent, we can start from 1 or 0, I guess. Our first term is 2/3, we're starting from 0. Our R is whatever this thing is. So it's 1/3 x to the n. And the tricky part is that there is a minus sign here, but the formula for geometric series already has a minus sign in it. So we take like just this positive 1/3 part. What's up? Why is there a negative? Like the negative here, or on the bottom? So I'm saying like this thing is positive 1/3 x rather than negative 1/3. Oh, that's not very clear. Like then negative 1/3 x, because the formula is already 1 minus r. So because that like minus sign is built in already, we don't carry the same like negative sign down. I'm probably not explaining it in the best way possible. But I'm saying this because if you had a plus here, then you do have to flip the sign. Because it needs to be like minus r. So if you, it's my hypothetical situation, if we had 1 plus 1/3 x, you could rewrite that to make it match as like 1 minus negative 1/3 x. That's what you'd have to do. And then you would get a minus sign inside there. Because like that part has to be a minus sign. But we don't have that situation, so we don't have to worry about it. I'm just going to give you a warning for future problems. So I think we can call this our answer for that question. I haven't done these in a little bit, so please tell me if you do have the answers, tell me if I'm wrong. Okay, yeah. I'm gonna erase the board quick while you do that. The answer is different. Yeah, if you could. I didn't determine the interval of convergence. That was bad. So the book's answer, I think it's the same. It does look different though, for sure. Let me explain why I think these are the same. And I completely forgot about the interval of convergence part, so we can talk about that too. Okay, so I just copied on what the book said is the answer, and the reason these are the same, so personally, I think this format sucks. I kind of hate it. I would so much rather leave it in this format where it's very clear what A and R are, but if we wanted to, we can manipulate what I got and make it into this form. So first things first, this, no. The first thing I'll do is worry about the exponent of n. So 2/3 will stay the same. we have all multiplication and division inside here. Yeah, that's what I was just debating in my headpen box with like, why isn't this 3 come out here too? So I do this power of n first to make it maybe flow a bit better. I'm gonna distribute this n exponent to the x, to the 1, which won't make it a difference, and to the 3. 1 to the n is just 1, so I'm not gonna even bother writing it. Now, 2 times 1 on the top is just 2. 3 times 3 to the n on the bottom is 3 to the n plus 1, using exponent rules. Times x to the n. And now, what the book does is, this summation only cares about things involving n. This 2 here does not involve n. We're allowed to take it out front. Like the 2 has nothing at all to do with n, so it doesn't change the value to bring it outside of the summation. So that's why these two things are equivalent, because you can rewrite it if you cared to put it in a format that I think is objectively worse. And kind of the weird thing is, we could have taken that 3 right there and also brought it outside of the summation for the same reason. But they wanted to make it 3 to the n plus 1, which is also valid, but weird to me. And this makes the next part really unclear with finding the interval of convergence. It doesn't really have a name with that summation. I don't think it does, at least. Summations, they're called the linear operators, I want to say, if I'm getting my terms right. And every linear operator has that property. Do I want to take a 5-minute break? I'm good to go, but if you need to like take a break, I can do something else in the meantime. So it's up to you. If you need to go and do something for a bit, it's no worries, but if you're good, then I'm good. Oh, no, my mic is on the charger, so there's nothing else to do with that. So yeah, then to the... I do want to say one thing about the... Or do you already understand how to get the interval of convergence here? Because I forgot to do that part of the problem. Okay, yeah, so let's talk about that before we move on. So it's the same rules as for any geometric series. The absolute value of r has to be less than 1. And so I'm going to use this form because it's very clear where r is here, which is why I like it. The book's form, you'd have to... It's not clear at all what r is without doing some manipulation. So just by looking at this, we can see that r is whatever is the power of n. Yeah. So 1/3 x is r, so we just do the absolute value of 1/3 x is less than 1. And we can break the absolute value out into like 2 inequalities, like -1 is less than 1/3 x is less than 1. And then you multiply this thing through by +3 to get rid of the fraction. So -3 is less than x is less than 3. And you have to check endpoints, which is annoying. For geometric series, do they never work? I think they never work for a geometric series. I wouldn't say it like that critical. you can set the x such that it's always convergent. If your x is between -3 and +3, it will always converge. If it's outside of that range, it diverges. Or it's inconclusive. Well, no, it diverges, I think. So yeah, it depends on x whether it converges or diverges, I would say. Is this song using the DS, like the Nintendo DS, like when you boot it up, that sound? No, I think it's just a piano sound. Never mind. I am debate like, do we need to check the endpoints, or are they never included for a geometric series? I think they're gonna probably never be included. I don't quote me on that, but just like for any other power series, we do need to think about the endpoints of this interval that we got. Never included? Okay. So it's good to consider, but I think for these types of geometric series, the endpoints, you're never going to get a convergent series with the endpoints. So if we plugged in -3 for x, yeah, that would diverge by the alternating series test because the limit isn't 0 here. Okay, yeah. Yeah, what's up, Critical? Oh, true, Fembucks. Well, -3. And +3, you divide by 0. Oh, but it's the absolute value that we care about. Is it? That part I'm a little bit unclear on what's -3, but yeah, if you tried to plug in +3 for x, you would be dividing by 0. Difference between alternating series and ratio test when both of them are alternating. No complex numbers of modulus 3? Oh, I guess, yeah, underscore. So the difference between alternating series and ratio test, if it's factorials, jump straight to ratio test. Otherwise, try alternating series test first, in my opinion, because it's quicker. And if that doesn't work, then do ratio test. The alternating series test, it doesn't, if the limit that you get as n goes to infinity looks too hard, then just do the ratio test, basically. It might still like technically be, it might still like possibly work, but you shouldn't get limits that are that hard to evaluate. Hopefully. Okay. Yeah, next problem. What do we have here? X squared. Now these are where it gets a little bit harder. It's the 4th plus 16. How do we deal with these? Hey, Cosmolano. Operator algebras. I've never heard of those, no. I've heard of operators and I've heard of algebra, but I don't know about the two combined. Yeah, I'm not sure who'd even like point you to for that. How does this? I think we can do the same thing. with the 16. Just an algebra of operators, bro. That's fair. Algebra is not at all my forte though. So yeah, critical. I would start by doing the same thing with factoring out the 16. And I also reverse the order inside the parentheses, which is, it doesn't make a difference. And I'll do the same thing where I write this bit as a fraction. This is where I'm getting a little bit unsure. But I think this is still how we handle. I'm just worried that we have an x squared for our initial term. It might be okay though. And we do have that situation that I mentioned before now where it's a plus on the inside. So I wouldn't normally do this if I was a student like doing my homework or something. But just to make it clear what's happening here, I'm going to write as minus a negative. And hey, yeah, Chic, you have a little homework question. You can factor it in C and can then convert it to R. Is that your homework question? I'm not sure what you mean with that. So if we take this thing and plug it into the formula for a geometric series, do we get something that makes sense? I'm worried about this x squared part. Again, I'm a little bit rusty on these. You asked me about. Oh, sorry. Oh, like factor with complex numbers. That's the I mean, you probably could, but the instructions for this person's problem is finding the power series for this thing using geometric series. So I don't think we want to use complex variables here. Separate algebra can have non-commutative multiplication rule. Oh, okay, yeah. If underscore wants, they could try it. I'm not touching that. I think this might be okay though, because we can do some rewriting here. I'm going to distribute this n exponent. Yeah, exactly. Critical. If you have a plus, it converts to minus. Letting u equals x squared over 4. We would sub the variable out in front, right? I think, what am I writing? What I'm thinking is I just want to split up the minus 1/16 part to the n and write the x to the 4th as x to the 4n. Is that... Ooh. Do we need to do like a change of variables like you're saying, Femvox? That feels like we shouldn't have to. It might help me like see what to do, I guess. But this is... This is unclear. Or can we just not care about the coefficient here and just still see where this bit is less than 1? Let's see if Paul's notes addresses this. Oh, ha, I see. Yeah, okay. Um, wait, what? Is this considered a hard problem? Uh, I don't think so. I just haven't done these in long enough, so I'm forgetting what the tricks are. I think I just found what I was missing though. Um, oh, okay. Yeah, okay. So, the thing that I was not realizing, I was just worried that this x squared, what am I, oh, I'm selecting, okay. I just, okay. I was worried that this x squared would mess something up when we go to find where it's convergent. But I forgot this summation only cares about n again. So x squared, it doesn't even matter. We can still just consider this part inside the parentheses for where it's going to converge. And hey, syntax error. Sorry, I saw you typed something about it. I was like, worried I was doing this problem wrong. You want a 7 for math / computer science today? I was in prison, so I don't know what I got. Hey, that's still huge though. That's awesome. Congratulations on that. And I'm in pain because my wireless microphone died. And so if I get up to go to the whiteboard, you won't be able to hear me. So yeah. You're in pain. I'm in pain. Oh. But yeah, here we can take the absolute value of this. -116, we can just make it positive. X. Yeah, I mean, we just make it positive. I don't want to overthink this. And then multiply everything through by 16. And then we're going to want to take the 4th root of all this. It's basically your first term of the series. Yeah, this is just me using my mouse right now. That's also what I was doing for the reading group there. But you know, my normal handwriting is so bad, this doesn't even seem Oh, this is where the exponents get tricky. So yeah, critical. We could absolutely take this thing here and put it outside of the summation. To your question. The issue that I'm running into here is I want to take the 4th root of each side, but the 4th root of a negative number is a no-no. It's like taking the square root of -1. And if you want to deal with that without too much hand waving, we have to deal with this power while we're still in the absolute value. So I'm going to rewrite 16 as 2 to the 4th, which is true. I left some x's in the sum. We could take this x completely out of the sum. It has nothing to do with n. The x here has to stay, but I think we can use just this chunk to figure out our radius of convergence, because that's the only part that relates to n, is my rationale here. Okay. No, this is like a tricky one, I guess. Okay, so yeah, to deal with this exponent stuff, I'm gonna now write this as 1 over 2x to the power of 4, just grouping things based on their exponents here. Even this step is a little bit sketchy, isn't it? I'm still implicitly taking the square root of -1 if I do what I want to do. Like, what I want to do is this right here. But I think I just said the 4th root of -1 is -1 because of that minus sign there. Like, I know what the answer should be, it's just justifying it. Like, this is okay to do, or like, it'll get it to the right answer, I just think for the wrong reason. Can I say, okay. Evil 1.8, yeah. Okay, this feels kind of dirty, but like x to the 4th is always a positive number, and even if it wasn't, the absolute value of this thing is equal to the there. Before we even consider whether it's less than or equal to 1, I'm going to say the absolute value of this thing is equal to the absolute value of this thing. Which feels really cheesy to do, but I think it's a true statement. And it avoids this negative sign business that I'm apparently struggling with. I've had this issue before. And then we take this thing and set it to be less than 1. Which this feels kind of stupid, but like, I think it's okay. Oh, wait. You know, now look back at Paul's notes. Oh, wait. I'm overthinking this, I think. Oh my god. Okay. Let me... Sorry. Critical. I guess this is maybe a harder problem. There's just some subtleties here that are a little bit difficult to deal with. Just for fun, I'm going to take the x squared over 16 out of this of the summation here. That's not the important part of what I'm about to do, though. I'm going to pull this negative sign out of the exponent by saying this thing is equal to -1 to the n times 1 over 16x to the 4th to the n. And this is an alternating series. The -1 comes from that minus sign right there. I can write a step between these two. So -1/6 over 16x to the 4th is equal to -1 times 1 over 16 x to the 4th n. And then I distributed the n to the -1 and the n to this entire thing here. Hey, Exo Gaming, how's it going? So that's how we can write it as -1 to the n. Good to hear. Yes? Okay. And so I think this is where we switch gears and think about this as an alternating series more than a geometric series. Yeah, I play games. I have gaming days on stream. This feels unnecessarily difficult. Oh my god, wait. I forgot. The absolute value of two things multiplied is equal to the absolute value of one thing times the absolute value of the other thing. Wait, let me look that up. Absolute value properties. That will make it so much easier. We're trying to find the power series or representation of this using geometric series. And there's just this negative sign is giving me issues with how we actually deal with it. And I think we can make the claim the absolute value of A times B is equal to the absolute value of A times the absolute value of B. And instead of doing this alternating series crap that I was just talking about, we can go back to thinking about it as a geometric series. If we take this thing as our R, 16x to the 4th, we can say this thing is equal to the absolute value of -1 over 16 times the absolute value of x to the 4th, and we set this thing to be less than 1. And the absolute value of 1 over 16 is just positive 1 over 16. That's how we deal with it. Okay. We still have to be a little bit careful here. Multiply each side by 16 first. Oh, why? I read that as what are we trying to solve? Why are you trying to solve? Yeah, because we like to, I guess. And now I'm going to say the absolute value of x to the 4th, the same as the absolute value of x to the power of 4, is less than 1. And now I'll take the 4th root. Oops, 16. The 4th root should preserve inequalities, right? We don't flip. I'm going to say it does. Is less than 2 if we take the 4th root of each side. And then we get -2 is less than x is less than 2. Can you send me the answer to this one, though, too, Critical? Because I want to make sure that I at least got to the right conclusion. Getting, like, this is the conclusion I know that we should have gotten the entire time. It's just actually showing it mathematically is the hard part. Okay, the interval is right. They write it in a different way, which is fine. We can get it in that form. Let me copy down what that form is. So I explained this terribly, and I apologize for that. So I can back up and go back through. You don't get the interval part? Like, you don't get how the book got their answer, or you don't get how I did this part here? I assume you mean this part here that I just did. My method? Okay. So there's probably a different way to do it as well, but we have the absolute value of two things being multiplied here. And the absolute value of two things multiplied is the same as taking the absolute value first and then multiplying after. And I'm doing that because of this pesky negative sign. So we're able to group the negative sign with the 1 over 16 and then say the absolute value of negative 1 over 16 is positive 1 over 16. And we have to not be too hasty still because... Oh, sorry. This one over here, that's from a geometric series. We want this thing to be less than 1. So yeah, that's why I said it'd be less than 1 in solving for x. So yeah, forget everything I said about an alternating series. This is just using the geometric series stuff. Hey, X factors, solve for Matt's last theorem. I think someone already did that. Also, I'm getting my Fermat's theorems mixed up. But yeah, dealing with that negative sign and the power of 4 is... They're both super weird things. And they lead to some unintuitive math. I saw someone with a Discord name, whatever, posted something like 10 minutes ago. Are you listening? I forget who this is. Right, yeah. That's how you can do a 4th root there. Just square root it twice. And now that I took the 4th root, that's when I deal with the absolute value. Because otherwise you're 4th rooting negative 1. Or square rooting it. If you're doing it your square root twice. Or it's... Yeah. Yeah. I don't know how to do that one either, X Factor. Give me 1 minute, Critical. I saw someone else post a question in Discord and I just want to take a little look at it. I don't think I can do it. Yeah, sure. It should only be a few minutes. The person posted... this and then this, but I don't know. Determine the polar form of each of the quadratic forms and write its matrix in the canonical basis of R3. I don't know. I don't know what this means, to be honest. I'm not sure I can do this question. It seems like a translation as well, so I wonder if something's slightly off. 1 plus 1? Oh, that one I know. It's 3, clearly. You know, I should be even sassier and say that it's 10, because I'm going to assume that you're talking in base 2. So yeah, whoever this is, I'm sorry. I don't know if I don't think I know how to do this. I don't know what all this means, I guess. Um, okay, Critical, I'm just gonna go right back to your question if you're still listening. I'll at you in a second. I don't see a type. Math is kind of entertaining. Oh, well, thank you, X Factor. Yeah, I'm normally up at a whiteboard solving these problems, but my mic died. So I'm just using Paint right now. My normal kind of shtick is I do math help on Tuesdays, Thursdays, and Saturdays. In the first part of Saturdays to become like a physics reading group, but and then on Wednesdays and Fridays I play games. Critical might have gotten up and done something. I see we can do I guess +3 -3 trick here. Oh, you are here. Okay. Explain gravity, I dare you. Well, every atom shoots out little gravity particles that somehow attract other particles to it by just a little bit, and you get a bunch of particles together and they act like one big particle. Seems problem yourself. Oh, okay. Sounds good. So I would simplify this before even trying to put it into geometric form, because the x in the numerator, like this x minus 1 in the numerator, makes things unclear to me. You probably could still apply the formula, I bet. Meaning life, eat pizza. Easy. I think that we could do a little trick here, though. I notice we have an x plus 2 on the bottom. And what if I did anything up top to get us an x minus 1, like saying +3 -3? So I haven't changed the value of the equation because I'm only adding 0. But -1 + 3 is +2. So I could say this thing is x plus 2 minus 3 over x plus 2. And the neat thing here is, yeah. Oh, so maybe you've even seen this trick and I'm explaining to you something you already know, but I'm going to split this thing up based on the numerator, and we'll get a nice like cancellation here. Where x plus 2 over x plus 2 is now 1. And now this is the exact same as the first problem. Oh, no, it's not. It's really close to the first problem. And whatever we get for this, we just do 1 minus that. What happened to the -3? I put the minus sign down here. It's like that minus sign is that minus sign. So only thing about this part as the part that is going to be a series now. Let's get rid of that, or let's factor that 2 out. Expected, this is, the problem is to find, oh, thanks for the follow. We're taking this function here in black and finding the power series representation for it using geometric series, which is something that you normally do in like a calculus 2 class, depending on the how things are organized at least. So we have this bit in geometric form now, so we can apply our summation formula. Notice this 1 minus 0 is still just on the outside, like it's fine there. 3 over 2 minus 1/2 x to the n. And now from here we can do our normal procedures to find the interval of convergence. Which the 1 minus has like no effect on. We can just worry about that bit there. You can take out the 3 over 2 if you want. I don't know how the book likes things. Oh, take out the 1 to make it alternating? You can, yes. Based off how we did that last problem, though, I wouldn't. I would use the same identity as last time. Make that less than 1. Adding negative number to equal positive is calculus. Like this thing I did up here, or maybe something else. Yeah, so we only care about the minus 1/2 x, as you say. And so I'm going to do the same kind of like product of an absolute value of a product identity here. Split up into 2 absolute values, and we know the absolute value of a half. The absolute value of negative 1/2 is positive 1/2. So we just end up with this. And I'm going to multiply each side by 2. And then deal with the absolute value. So we end up with that. Actually, I noticed your book has been putting the interval notation with parentheses and brackets. So just to make sure that you're on the same page with that, we could translate this inequality into that interval there. These are like completely interchangeable. So is that okay with you? Oh yeah, sure. Yes, there might be a different way that you can do it if I could figure it out, but yeah, exactly. I asked myself, we want x plus 2, but we have a minus 1. So what do we need to add to minus 1 to make a positive 2? And the answer to that is 3. That's what you would have done? Okay. Exactly, yeah. And we're doing that because we want this x minus 2 over, or x plus 2 over x plus 2 cancellation. Long division is the other way. Yeah, that's what I was trying to think of. No, yeah, it's a very weird trick. You can use it for, I mean, you can use it anywhere, but it comes up, it can come up in integration as well. Actually, yeah, you do the, if you had to integrate that, you can do the same exact trick and get a simpler integral. Yeah, sure. Go next. Okay, let's read the instructions first for once in my life. Express the function as the sum of a power series by first using partial fractions. Find the interval of convergence. Ooh. Okay, I see we're going to take the most strict conditions then. What happens if they have no intersection? That'll be interesting if we get a situation like that. Let's not worry about it yet, though. So we have this. They want us to do partial fractions on this terrible thing. Oh, wait. Are we getting... No, we don't. Never mind. I thought we got a cancellation. First up, before we can partial fractions, let's factor this thing, because it does factor. It's not an irreducible quadratic. We get x minus 3 times x minus 1. And now we're as ready as we can be to partial fractions. So let's dive into it. Gonna do it the way that I usually do, which is making this thing equal to a over the first part of the denominator, since these are just linear factors here, plus b over x minus 1. And now we multiply each side of this thing by the denominators here, or by the denominator. It's all the same, I guess, but we multiply by x minus 3 times x minus 1. And we get a bunch of cancellations, thankfully. So over here on the left, this thing cancels entirely with the x minus 3 times x minus 1, so we only get 2x minus 4. Over here with a, the x minus 3 cancels with the x minus 3. The x minus 1 stays there, though, so we have to include that. And then for the b, the x minus 1 cancels with the x minus 1, so we just have the x minus 3 to deal with. So this is, as far as partial fractions go, this is about as nice of a situation as they could give us, because it could have been a lot more work. I'm going to multiply the a's and the b's into their parentheses. And then let's group things by the power of x they have. So we have an ax plus bx. I'm going to say a plus b times x. And then we have constants minus a and minus 3b. A plus b is 1. Oh, a plus b is 2. Yeah, so now we can equate coefficients. So the coefficient of this x must equal the coefficient of this x. Oh, a equals b equals 1. Okay, cool. So from the x's, we get a plus b equals 2. From the constants, we get negative 4 equals negative a minus 3b. And if I get critical, when you have a system of equations like this, do you do substitution or do you add the equations together? Or both? You isolate? Okay, we can do that. Let's take this equation and subtract the b over. Why not? So we get a equals 2 minus b. Let's plug it in over here. So negative 4 equals negative from that sign, 2 minus b minus 3b. Distribute the negative sign. Negative 2 minus 2b, or not to b. Add this 2 to each side. You get negative 2 equals negative 2b. So b equals 1, as Fembach's prophesized. And so if b equals 1, it looks a lot easier to deal with this equation up here. So we get a plus 1 equals 2. Subtract 1 from each side, and we get a equals 1 as well. All right, so partial fractions, successful. Um, so from this step all the way down here, this thing is equal to, I guess, this thing with A and B plugged in. A and B are both 1. So we get 1 over x minus 3 plus 1 over x minus 1. Now we have two separate geometric series to get here. Let's do our good old factoring trick on each of these to get things in the form we want. So here we have x minus 3, but we want it to be something minus x. So I'm definitely factoring out a negative sign. And because of that 3, I'm going to factor the 3 out as well. So this negative 3 becomes positive 1. This plus x becomes minus a third x. And then over here, similarly, we already have the 1, but we want to flip these signs because we want 1 minus x rather than x minus 1. So let's factor out a negative sign. And I'll do my little like extra rewriting that I wouldn't normally do. I'll bring this negative 3 up top to be negative a third. 1 minus 1/3 x plus this negative sign can come up top to be negative 1 over 1 minus x. Now let's plug now let's make it a geometric series. N equals 0 to infinity. Negative a third times positive a third x to the n plus, now this other one gets its own series, although if I know we can actually combine them in a second here if we wanted. Negative 1 times x to the n. And so if we care to, these are both summations starting from 0, and they're joined by a plus. Well, technically there's a negative 1, but we can combine them into one summation. Your book might not go, well, ooh. Ooh. I think we leave it like this for now. So we do have to find the interval of convergence here. We can do some fancy writing stuff later, but I think this will be the easiest to find the intervals with. I see maybe about to type something. Oh, yep. Yeah, that's the entire point of doing the partial fractions, so that we can now apply our same geometric power series that we've been doing. All right, so if you're otherwise with me then, we have two series summed together here. So if the only way for this entire thing to converge is if each of these series converges individually. So we need to find where each of these converges on their own and take like the most strict set of requirements from each of them. It might also be called like an intersection, but I don't want to use terminology that you don't know. Do I have room off to the right? Oh, I do. Okay. So considering just the first series in a vacuum, not caring about the second series. Let's do our good old take this rate and set it less than 1 trick. This one, we don't have any weird things with powers of x or negative signs, so let's just break out the absolute value. Now multiply everything through by 3 to get -3 is less than x is less than 3. So that's our interval for one of these. Now let's look at the other one. -1 times x to the n. So do our same trick. Absolute value of x is less than 1. This one's just a one-step problem to break out the absolute value. All right. So one of our intervals is between -3 and 3. The other interval is between -1 and 1. We can just look at this and say that the numbers between -1 and 1 are contained within -3 and 3. So we should take the smaller of these. And we can draw it on the number line, which might make it a bit more clear. If this is 0, 1, 2, 3, 1, 2, 3, I mean, hopefully this makes it clear. This red series on the left converges for -3 to 3, all of these things. But this blue series on the right only converges for -1. That's not the same blue. Only converges for -1 to 1. So if we're summing these two series together over here on the left, we need them both to converge at the same time. So we want to find the overlap between these two things is maybe the better word. And their overlap is right here at -1 and 1. So the interval convergence for the entire series is -1 is less than x is less than 1. And the overlap piece is important because in theory, you could have a series where like, or you can have like two series summed together where like one is like this and one is like that, in which case, you know, you still take the overlap. Or you could, in theory, have a series where there is no overlap. In that case, it will just always diverge, I think. That's my theory, at least, for how we do this part. I want to ask if you can check the answer to this one too, though. Oh, thank you so much, Underscore, for looking at that problem in the Discord. All right, for this example, like I made up here, this would be convergent between those two things, yeah. And divergent everywhere else. Because if one of these series blows up to infinity, it messes up the entire thing. So they both have to converge at the same time. And yeah, the bottom right is divergent because you can never find a value for x that works for both at the same time. And maybe like this number line is values for x here, I should say. Awesome. Sure, we can do set 17. Someone says find a power series representation. Is this chapter about geometric series? Like, should I still be thinking about geometric series here, or are all bets off here? Yes? Okay. So yes to same chapter, geometric series. I think this is partial fractions, unfortunately. Is there a trick? No, not that I see. Yeah, I don't see a trick. So let's see what partial fractions gets us, I guess. Well, is this even going to help us that much? Yeah, it will. Will it? I don't think partial fraction is going to help us. How does this work? Most beautiful area of math. I found an example problem. Let's like this one. Ooh. I mean, I'm gonna say the caveat that beauty is subjective. So I would say, I guess, differential equations. Other people could very validly disagree with me, but yeah, that's my answer. Okay, so I'm looking at Paul's notes. There, we gotta pull out some tech here. So I'm looking at the example from Paul's notes, which I think is more or less the situation that we have here. So partial fractions might help us. Well, I'd say geometry is not beautiful. I think the geometry that's at least taught to like a elementary and high schoolers is not to me. I think we're gonna have to notice that this series is the derivative or the integral of some other known series, and we might need partial fractions to do that. Because 1 over 1 minus x, we do know that series, and this is kind of like that. but we have an x in the numerator and they don't in Paul's notes. So I guess partial fractions. Ugh. Geometry is the most beautiful? No. Well, I mean, I think geometry gets cool, but like, I guess what you call like elementary geometry. I'm not a fan. So I'm thinking about partial fractions because this a and b are just going to be constants rather than the x. And then we can look for tricks like on Paul's notes, I guess. Even this is really annoying. Riemannian geometry? Really? Not like a... I guess like Euclidean? I don't know. Honestly, even Euclidean geometry can be cool if they don't make you prove the most stupid crap about triangles no one cares about, I guess. Oh, this partial fractions is not so bad, is it? A plus 4ax plus b. So it's just the same technique that I've been using here. Equating coefficients, we get 4a equals 1. And a plus b equals 0. You heart triangles? Oh, wow. Random psychology made no sense to me. Oh, you're saying that's the part that you don't like? Okay, that's fair. I mean, I guess it means you like some other part of geometry more than. So from this first, we're gonna get a equals 1/4. Plug it in over here. We get b equals minus a fourth. Oh, partial fractions. Yeah, partial fractions suck. Round of geometry is your favorite. Oh, okay. Yeah, partial fractions they're just busy work. It's good to know how to do it, but being made to constantly do it over and over again is like meh. But yeah, so I found a equals 1/4, b equals minus a fourth. Let's plug it into here. So this is the 1/4, 1 plus 4x minus 1 over 4, 1 plus 4x squared. 4 hours a night for 2 weeks straight. Yeah. All right, so this one on the left here, that's good to go. Like, we've been doing these all the time. This one is where we have to use some finesse and think about derivatives and integrals. Oh, thanks for the 10 bits. I appreciate that. 4 hours a night for 2 weeks straight. Yeah, I hard agree, Cosmolano. Okay, so yeah, I realized that from Zach's raid. It's like, oh, okay, I guess Brian changed his name again. Then like I doubted myself the last second. I was about to say Brian, so I was like, oh, okay, let's just say Noble Penniless. In case I was like misremembering. You know, you were singing with that name for like, I feel like you had a good streak going there. But it's classic Brian name change. Which, I mean, you're free to do whatever you want. Okay. We got to figure out what this thing is a derivative of. So I'm thinking about 1 over 1 minus x. Let's take the derivative of this and look at what the problem with it is, because it's not going to be exactly this, but this could help us figure out how to modify it. That derives to negative 1 minus x squared like that. So we need to flip this sign in the middle here, which we can do, and we need to stick a 4 in front of this x, and let's see how that comes out. So let's see. So the 1 over 1 minus x, it's just a known series, I guess. Like, it's the most basic form of a geometric series. So you really don't have to do this step. You could probably skip straight to this step if your intuition is good enough, but I was showing this because this is like the type of thing we need to think about. This exact thing won't be right, so we're gonna have to modify it in some way. But yeah, no, we did the partial fraction above to get rid of this x in the numerator, and that's why now we can think about the derivative thing, I think, Brian. So if we derive this 1 over 1 plus 4x thing from chain rule, we get a, well, it's not do the chain rule first. Let's start with just deriving that bit there squared times 4. That's nearly perfect. The only issue is we have a times 4 on top here, and this 4 is on the bottom over here. So we can be a little, like, cheeky. And we know we want to end up with a 4 on the bottom, but we need to cancel out this 4 on top. So I'm going to multiply each side by 1 over 16. Yeah, exactly. So we get that 1 over 16. Oops. 1 plus 4x prime is equal to, wouldn't you know, 1 over 4, 1 plus 4x squared. The squared part? No, we specifically want the squared part because it's going to match with the squared we have here. Or unless you mean like with 4 squared is 16. Sorry, I might be misinterpreting you. Okay. As long as you're on board with me. So, what this lets us do, the entire point of doing this little exercise here is that we can now we know how to find the power series of this bit inside. So we can do that and then take the derivative, and then we're in business. So the task that's remaining from this piece of work here is to find the power series for that and derive it. There will be a 1/16 in front, but that's fine. I'm going to take this little like identity that we made here, because we know we have the 1 over 4 times 1 plus 4x squared right here. And we also have it here. So I'm going to replace it with this little derivative thing that we have. So 1 over 4 times 1 plus 4x. This is the same as the first term from the left side. Now minus, this is where I'm using the identity. One plus 4x prime. That's what I said, right? Yeah. So all I did was substitute this out for the thing that we just found. Oh wait, did I mess up with the minus the fourth? No, I included the fourth. Yeah, so we have like we have things that we can work with now. We need to find the power series for this. We need to find the power series for this. And I think we can combine, like, it's basically the same thing, these two series. So we can do the work for this one and then reuse some of that work over here. Well, it won't be that bad either way. So let's just dive into this series, I think. N equals 0 to infinity. This first one, oh shoot, I should have rewritten it. No, wait, it's already written in the right form. No, never mind. I'm not going to go through all the extra rewriting that I was doing before, but our first term is the 1/4 there. And then we have a plus here, so we need to remember to flip the sign and say it's minus 4x to the n. So that's for the first part of the series. The next part, we need to be careful about how we write it. Because we're writing the series for the thing inside the parentheses here, so our summation should be inside the parentheses as well. N equals 0 to infinity. That's a plus, so we're going to make it a minus 4x. And our starting term is 1, so it's easy, thankfully. Prime. All right, nice. It doesn't look that pretty on the right, but we can deal with this. The parentheses in front of the sigma. That's because we have this prime here. The prime applies to everything inside of the sigma. So in this next step, this first part is staying the same. We have to take the derivative of an infinite sum, which is a little bit of a weird thing. Now, thankfully, summations and derivatives, they interact nicely, where you can just derive things term by term. This gets represented in different ways, but we can just treat this like n is just an integer. So we can treat this as like, if we had negative 4x cubed, how do we derive that? You know, you just do the power rule, subtract 1 from the exponent, squared, and then chain rule, multiply by negative 4. We can do the exact same thing here, just instead of 3, we have an n, and that's completely fine because n is just a number. So the n comes out front, minus 4x, now to the n minus 1, because you subtract 1 from the exponent, and then chain rule, we're going to multiply by negative 4. Now we should do some cleaning up on this. Does this change our starting term? We could rewrite this, but the way it's written is fine. Maybe it's not the best way to write it, but let's not make things harder than it has to be for now. So this left series will stay the same. This one over here, let's clean it up a little bit. This -4, it can come out front and get multiplied with a -1/16. So negative times negative is positive. 1/16 times 4 is 1/4. Then our summation stays the same. So you could call this our power series, but we need to find the interval. Wait, they just want the radius of convergence. Really? Okay, so now they're asking for radius of convergence. Okay. This will be the same idea as last time, where we treat each of these summations individually and find where they both converge at the same time. That series on the right isn't quite a geometric series, though, is it? How does that work? We can still find the radius of convergence, I guess. Okay. Let's start with the easier one. Yeah, it has a lot of steps. So we take the absolute value of -4x and let it be less than 1. Solve this for x. Let's use our product of or absolute value of a product identity. Absolute value of -4 is +4. X is less than 1/4. Break out the absolute value. -1/4 is less than x is less than 1/4. All right. If you just stuck with the answer that I said on the final exam, if that will be accepted by your teacher. That's what I would write personally. Oh wait, is there simplification? I thought we couldn't combine these series. No, you can technically write this as one summation. It makes it less clear to me though. Never mind. Yeah, I was just wondering if there's some simplification that I was missing here, because they do look really similar, but invite back if she marks it as partial credit. Yeah, the thing about teachers or textbooks requiring a fully simplified answer is that the word simplified isn't very well defined in math. It means different things to different people. So I would call this fully simplified because, I mean, nearly. I mean, there's like one or two little cleanup things that I might do if I was like presenting it, but like, I wouldn't consider them significant at all. Even then, yeah. Yeah, but like I think this is an acceptable answer in my eyes. Partial isn't that, but it's the answer. Basically, I mean, yeah, what the book was doing, I think makes it more complicated, which is the opposite of simple. But some people do call that simplification. Yeah, I completely agree. Critical. So we have a power series here. We have to find its radius of convergence. just in general, this n here existing means that we can't use our normal geometric tricks. So when we open the radius and interval convergence of power series in general, we go back to the ratio test. I'm doing a good job estimating my space. n plus 1 minus 4x. N minus 1 plus 1 is just n. So let this be less than 1, and now we solve this for x. A equals sign isn't quite accurate, is it? So I'm going to do, oh, that's a 4x, sorry. So let's cancel these. We have a negative 4x to the n and negative 4x to the n minus 1, which, when we do that cancellation, we have the negative 4x on top. For n is less than 1. Now we can do the same, like, product of an absolute value thing. Like, my goal right now is to, this negative 4x has nothing to do with n. It can come outside of the limit as long as we separate it out properly. So that's why I'm starting with this absolute value, like, multiplication thing, because this is another instance where you have the absolute value of two things multiplied. I'm calling my first thing n plus 1 over n. I'm calling my second thing negative 4x. And now this unit can come out front of the limit because it doesn't involve n. N is always positive, so n plus 1 over n is always positive, so let's drop the absolute value there. Now this limit we know how to evaluate. It's just going to be 1. So we end up with negative 4x absolute value is less than 1. So I hope you're comfortable evaluating a limit like this by now. I feel like we've done them pretty often now. Yeah, exactly. So we need to get rid of the negative there. So we get 4 absolute value of x is less than 1. Divide through by 4. Break out our absolute value. Okay. All of that work to find this interval agrees exactly with this interval. So we get to save ourselves a bunch of work. We can just say they're asking for the radius of convergence. So the radius of that is just 1/4. Because they converge at the exact same values. This would be on the exam. Okay, well, that's good. It's a pretty hard problem. 2 hours for? Oh, wow, yeah, that would, that could easily be half an hour. I don't know how long I spent on it there. Like, if you're quick, it's half an hour on a test, I think. 14? Oh, okay, yeah. You shouldn't have one that hard, then. If you're good with that one, there's 2 more problems on this list you sent me. Is that going to be it for you for the day? Because I'm thinking I might make those my last 2 problems. Oh, you don't want to do it now? Okay. I think they're going to be a similar amount of work. um, all right, cool. I mean, if I'm taking a break, I'm taking a break until next Machine Math, which is Tuesday. So I'll go through these problems if you want to see them. But okay, okay. Unless you happen to catch like Penn or someone streaming as well, but Monday's your final? Like, yeah, isn't that not okay then? Unless you mean the Monday after next. Okay, yeah, sure. Uh, are you talking about the horizontal asymptotes for arctan? Oh, that's pretty good arctan right there. Yeah, I remember doing an arctan with like the root test with you. So it's if you're taking the limit as x goes to infinity, you do end up with pi over 2. Because of this horizontal asymptote thing. Yeah. For now, you're good? Okay. The problems that we did together? Okay. I guess good luck with your final then. Let me see. I think it's not like you've been studying a lot for it, so I'm sure you'll do well, but um yeah. I'm trying to think. It's like I think Penn Center. I don't know if he'll be open for math help, but I know he's doing the abstract algebra tomorrow at 7 p.m. Pacific time. Oh, and Ian Suki normally streams on Sundays as well, half an hour before I normally start. So if you do have some last minute questions, there's that like there's those resources too. You're doing linear algebra this summer. You don't know how hard it is? It varies by the class. Mine was not so bad, but I've had a rude awakening when I've tried to tutor students in linear algebra, and they're doing all sorts of crazy things. The linear algebra that I took, it was like it started off with just like, how do you multiply two matrices of numbers? So you can define how this multiplication would work, and it's a lot of arithmetic, but it's not so bad. Harder than calculus 2. I don't think so. For a first semester linear algebra class, should take cubic algebra. I had a friend specifically who I remember who like his linear algebra class was just a breeze for him, but he struggled hard with stats actually, and I had to give him a lot of tutoring there. So there is a version of this class though that does get taught, where it's very proof based, and it's a lot more it's like maybe abstract or rigorous, or there's a couple different words that you could like call it, but it really depends on the school. The version that I took wasn't so bad. I would say it's not as bad as calculus. It is like a different way of thinking about things. Like you have to, you know, learn about vectors and how you can combine them, and how, like, I don't know, if you have a vector like 2, 1, and the vector -1, 3, you can conceivably add and subtract combinations of these vectors as much as you want to get around the entire XY plane. Like that's a concept in linear algebra that you'll probably get taught. As well as like you can go down there, and that's called like span. Why do people learn this material? Linear algebra comes up a lot actually. It's one of the more useful types of math that you can learn. The thing that I always hear about it is that machine learning and AI, it's used all over the place. I can't tell you exactly where, but it's used a lot there apparently. As my God, I'm about to hesitate again. As Brian says, it's also a system of equations that are linear. Like even with the partial fractions, you can use linear algebra to solve it. Yeah. From what I've heard, AI is really heavily reliant on linear algebra. I believe physics is as well. Really, anything that's going to involve vectors is going to have some kind of like linear algebra component, as far as I know. But yeah, you'll learn, like, even with those partial fractions problem, we have what, like 2a. This is going to be the exact same thing, but it's okay. 2a plus b equals 1, and a minus b equals 3. There's actually a matrix way of expressing and solving this system of equations that you almost certainly learn about. It's like you would take the coefficients of the a's and b's and put them into a matrix. And then you would do matrix multiplication with the vector a and b and set it equal to 1, 3. So you don't have to worry about like how you actually do this yet, but like you'll see things like this, and it's not so bad to actually do. It just looks a little bit complicated. Oh, graphics as well. Like, yeah, that's a really good one. If you want to like make a video game and you want to calculate like the shadow that's cast by your character flashing a flashlight at a table or something, that's linear algebra. Which I guess it kind of goes back to being related to physics. Yeah, I know Pinson in particular really likes linear algebra. And so you'll just be learning for the first time. I assume that he'll be able to help you out with whatever you need. If it's basic linear algebra, like stuff that I've shown you on the paint thing here, I can help too. But I'm very rusty on linear algebra. There are normally people around who know it though. Like I know that like Anders is good with it. I bet that like Underscore is good with it too. It's not my strong suit, but if you like show me some actual problems, I can tell you if I can do it or not, I guess. Once you actually get into the class. Yeah, my memory of calculus is a lot stronger as I practice it more. I took a linear algebra class, but I've hardly practiced it since, so I've lost a lot of it. Even then, I've tried to just tutor students in it, and they were taught it completely different than how I was taught. So it can be a tricky thing. Oh, you know what? Speaking of Pen Center, I see that Pen Center's playing some Zelda. So yeah, Critical, unless there's anything more for me, I might dip on out for the day. No worries. So I have questions to actually like work on as well for the stream. So even though it's a lot of questions, I'd rather have questions from someone who actually get helped by it than just me doing random challenge problems or things like that. Yeah, let me turn off the YouTube stream.